Today's objective is using similar figures to find measurements. Remember that similar means the same shape but different size. Also, the side measurements are proportional, which means you can use proportions to solve them, and the angle measurements are the same, congruent. So here's our example. Shape ABCD is similar to shape EFGH. So the first thing I do when I read this is I go and trace them so I know what I'm talking about. So ABCD, EFGH. I notice, okay, not only are they not the same size, they've been flipped over. So I can see that AB is the same as EF. AB is the same as EF. Okay, and I can do that all the way around. BC is the same as FG. BC is the same as FG. CD is the same as GH. CD is the same as GH. And then AD, the first and last, is the same as EH. AD, EH. So I don't really even have to look at the shapes to see what my corresponding sides are. I need to find the measurement for line segment EF. Here is EF. So I use the information given to find the corresponding side and then set up a proportion and solve. So if I need to find EF, I look up here and say EF, it's the first and second letters, it's the same as AB. So EF is the same as AB. And now I look and say, oh, I can do long side to short side here and the same as long side to short side there. And this is my missing one, so I'll put in an X. So I'm going to say, oh, actually I'm going to do short to long, because that's what I wrote up already. So 12 is to 16 as 30 is to X. Short to long, short to long. So first I'm going to look for a relationship. Does 12 go into 30? No. So I'm going to simplify and look again. Divide 12 and 16 by 4 and get 3/4. Hey, I see a relationship now. All I need to do is multiply by 10. So 4 times 10 is 40. If there wasn't a relationship, I would use cross products to solve if necessary, but I prefer to try to figure it out in my head. All right, here's a really good one. Triangle ECA is similar to triangle DCB. So let's ignore all of this information. So I have a big triangle here that has another similar triangle right on top of it. So triangle ECA, the big one, is similar to triangle DCB, the smaller one. So I need to do two things. I need to find the distance of AB, and I want to find the distance of AC. So once I find AB, I can add it to the 36, which is the BC part. So the first thing I do is I rewrite this as two separate triangles. I'm going to rewrite it so I have ECA. Here, ECA. I know this side is 20. I know this is 36 plus X. Do you see why that's 30? This is 36 and this is X, so the whole distance is 36 plus X. Now triangle DCB, I'm going to write that, and I know this base is 36 and this side is 15. All right? So if I need to find what AB is, that means I need to find the X part. I cannot just find this by itself because this is a side of this trapezoid, and this is not a trapezoid, it's a triangle. So I need to find it using the whole triangle. So I'm going to write my word ratio, and I'm going to compare side to base. So I'm going to say compare this side to base to this side to base. So I always write down the ones I know everything of first. So 15 is to 36 as 20 is to X plus 36, or I don't know why I wrote 36 plus X, but what's the property that says I can change the order? The commutative property. Hopefully that's what you said. All right, so I'm going to cross multiply. 36 times 20 is the same as 15 times the quantity of 36 plus X. Okay, do you see how I did that, cross multiplying? Now I'll do the work. 36 times 2 is 72, add a 0. 720 equals 15 times 36, 540, plus 15 times x, 15x. Now I'll subtract 540 from both sides, and I get 180 equals 15x. Divide both sides by 15, and x is 12. So that means the segment AB is 12. And the segment AC will be 12 plus 36, or 48. And I didn't tell you what the measurement was, so you would just put units if you wanted to write one down. You can use proportions and similar figures to find the measurements of objects using indirect measurement. So if there's something that you can't physically measure, you can use similar figures and figure it out. For example, here you are. You're bald. You are 5 feet tall, and right now your shadow, that's the shadow, that's why it doesn't have a face, is 8 feet long. The same time, you're standing by a flagpole, and you need to know how tall the flagpole is. And you don't know, but you can measure the flagpole as 56 feet long. So here's the flagpole shadow. The shadows are similar when measured at the same time of day. So you can use a proportion to find the height of the flagpole. Okay? So, you see how long your shadow is, you measure that, or have a friend measure that, you measure the flagpole, and then you can set up a word ratio. And I always write thing over shadow, because you know how I love to write the word thing. And the thing can be you, a flagpole, a cactus, a tree, whatever, something tall that you can't measure right now. And the shadow is always I always write the shadow in the denominator. You don't have to, but I always do, because I'm just consistent that way. So write the word ratio, write the proportion, simplify, and solve. So this thing over shadow is 5 over 8. This thing over shadow is x over 56. So 5 over 8 equals x over 56. Now I can't simplify 5 over 8, so I'm just going to cross multiply. 8x equals 280, because I did 5 times 5 is 25, 5 times 6 is 30, so 250 plus 30 is 280. Divide by 8, divide by 8. X is 35 feet. Therefore, the flagpole is 35 feet tall. And there's no way you could have just measured that. All right, that's it.